Yeah, good afternoon, everyone. Hope you have a good lunch. So this is going to be a hands-on plus presentation. So be prepared with your laptops. We are going to create instances, GPU on which we'll be running some Jupyter notebooks to gain hands-on experience. So we'll guide you step by step. So yeah, as you get prepared, just a second, I think there is some. Yeah, so as you get prepared, we are putting extension codes so you can charge your laptops. So if you can go to this URL to set up the notebooks because it will take some time to spin up the instance because we have a good amount of people here. So I'll guide you that before. So that's why we are going to spin up the instance now. And we'll start with presentations for some introductions to whatever we are going to do with respect to GPU, how to create LLMs, and all the stages that are involved in that. So by that time, the instance will be prepared. So that's why we are going to set up the logistics first. Go to this URL, tinyurl.com/casmel NVIDIA. Hope it is visible in the back. Can someone confirm? Yeah, thanks. क्या हो रहा है इसमें? Presentation mode क्यों नहीं आ रहा? Once you are on this URL, you need to sign up. So I'll tell you the setup. So this is one of the NVIDIA offered service similar to Google Colab, where people can spin up the instances. So it's similar because it gives you a wide variety of choices in terms of choosing a GPU and running your instances with the container from the scratch, etc. So we have allocated good amount of credits for this workshop on which we can do some hands-on. So once you go to this URL, you need to sign up. You can sign up with your personal email ID or your own organization email ID. It's agnostic to that. Once you sign up, you will be landing on this page. So the URL is tinyurl.com/casml-nvidia. And once you are able to sign up, you will be landing on this page. Yeah, you can take pictures. If anyone is facing issue, my name is Ayush, and I have with me my colleague, Dr. Manish, in the middle. So if you have any issues in spinning up the instance or getting to the URL, getting the sign up, he may help you. But most of the errors should be self-explanatory. Yeah, and also you can raise your hands. We are giving 5 minutes to set up this thing, and then we'll start with the presentation for 30 minutes. So this is going to be our agenda today. We are going to have some discussions on understanding the hardware. What does the key difference between CPU, GPU? How do we understand the system topology? Like once you have a cluster with you, a cluster with multiple nodes, or let's say a single GPU with you, or a single node with multiple GPUs. How do you analyze? What are the key things that make your LLM do perform well from the computation perspective? So that's what we are going to devote 30 minutes for that. And once we are done with that, then we are going to jump into LLM. The URL is this. on which you have to sign up, tinyurl.com/casmel-NVIDIA. And once you are able to sign up, you're going to go into this page where you have to click on launchables. And once you click on launchable, previous? Yeah, this is the URL. Yeah. क्या हुआ? ठीक है ना? Yeah, anyone? Can I change this URL page? Yeah. Yeah. I could have. Yeah. So let's start. Once you are landed on that page, you are going to see this screen. If you are not able to see the screen, please raise your hand. Once you are signed up, you should be landing on this screen. Okay, let me do. Yeah, if it is loading, it will take time because I said this is a lot of people that are going to spin up the instance at a similar time. So this is going to hog some amount of bandwidth or traffic on the launch, on the cluster who launches this. So there's going to be some time, but you will be in the end landing on this page where you have to click on launchables. So there are several tabs: GPU, deployments, team, billing, etc. You click on launchables, and then you're going to see this page where you will be seeing two instances. Like here in organization launchables, there is CASML-NV2, and there is another instance, CAML-NV-A100. So one is the H100 instance, and the other is the A100 instance. Yeah. Yeah. So can you repeat, sorry? Okay, is it still loading? You click on the launchables. Okay. Same issue. Okay.
Although it does show that up there.
Yeah. So you just refresh the page. You click on the launchables again. So it will load up. So that's the usual thing that we generally see. The systems are yet to be perfected. So you just refresh the page, click on launchables again. If you are not able to see this page, there are two instances, the ending with NV2 and ending with A100. The ending with NV2 will spin up H100 instance, and the A100 one will spin the A100 instance. So remember to click on launchable, and once you're done with that, you click on that title of the instance. You don't click on the copy, etc. So there are several options here to click on, but you click on this particular thing. You click, I will have this pointer with me, sorry. Yeah, you click on this title, Casmel NV2, and once you click that, you will be landing on this page. Again, this will take a lot of time to load. That's why we are doing this step before starting with our actual stuff. So you refresh the page if this is not working. And once you are done with this, you just click on deploy launchable. And then we'll start with the actual stuff. अच्छा रब नहीं करना ठीक है. Anyone not able to? Yeah, please. Can you be a bit louder? Yeah. So if it's an insufficient capacity, you can choose any other provider. So these providers are basically few cloud service partners or neo cloud partners, which which are hosting these instances. So you can, if your instance doesn't spin up, it is showing some error, then you refresh the page and or change the provider. So there are several providers and there is a arrow button here. So at the right end, you have a arrow button. You click on that, choose any provider which you feel like, and then we'll wait for some time. We'll come back to the presentation after that because it will take few minutes to spin up. Yeah, please raise your hand like if you are facing any issue which is not shown here. Yeah. You connect with the ISC Wi-Fi. So there is a ISC Wi-Fi which you can connect to, and if you're not connected to the ISC Wi-Fi, you can ask for password. If you have people here, yeah. So which network are you connected to, all of you? Like ISC networks? No, some of them are like connected with your personal hotspot. Maybe you can pin the message again so that it's at the down. And once you click on deploy launchable, you should be seeing this page. Let it run. We'll come back to the presentation now. Right? Yeah, you choose a different provider here. So here there are different providers. You choose Nebius, Lambda Labs, or click on this arrow where you'll see other providers. And if you are, so there are two types of instances, H100 and A100. If you are still not getting instances on H100, then click on the A100 one. We have separate GPUs which are allocated for this particular. Yeah. Yeah, so deploy launchable. Okay, can you show me there?
Will come at the top of one second.
Achha, you choose this Nebius or some, yeah, launch is not deploying. So now this is deploying GPU. Now you don't need to worry. Okay, वहाँ पे है. Right, are we good? Are we all good with this? Anyone not yet deployed instance? So once you see that, then you will see the deployment process will go on. It will spin up a VM. And on top of VM, it will install some Docker container, which is Nemo 25.09 Docker container from NGC, which is NVIDIA catalog for hosting containers. Okay. Yeah. Yeah, so you change the provider. So there are 4 providers that are being shown in this, but when you click on this arrow, it will give you other list of providers. Right? Right. So it will take some time to spin up the instance. Now, I hope it's fine with all of you. If it's still having some issue, we have Dr. Manish here, which can help you, who can help you. Yeah, so it's loading means here this page is still loading, so it will load in some time. But yeah, so now we'll start with the presentation and the agenda that we are trying to cover today. So we are going to understand how LLMs are developed. So there are several stages in LLM development. From scratch, why do you want to do from scratch? Because it will give you good insights on how things work when things are performed at large scale. It's not deploying.
It is giving the same RPC error. Same for you.
You change this provider, let's say set, and then do deploy launchable. Okay.
Now
it should.
It throws the same.
Yeah, try changing the providers or change the, select instead of A100 instance, select some NV2 instance. So there are 2 instances which are shown in the launchable. Okay, failed to create.
This is the error I'm getting.
Okay. You select some other instance. Instead of A100, you select NV2 instance.
Is it have to done with anything with the...
No, nothing with the laptop. It's only to do with the bandwidth of the internet. So my name is Ayush, and there are a few links here. One is my own profile, and the other is the GitHub, where all the Jupyter notebooks and presentations will be stored. So the URL is github.com/my GitHub ID ayushbits/LLM-development. You can scan this GitHub QR code also to see. And with me is Dr. Manish, who is my colleague and engages in a lot of stuff around scientific ML. Yeah. You're facing some issue? Manish is on there. Yeah, you click on launchables.
Now in the launchables also I'm not able to see the...
Yeah, here. Okay. So you try clicking on launchable 2-3 times, like it will come. Yeah, you go to the launchables and change the, instead of A100, select this NV2 wala instance.
Sir, it is showing out of stock.
Yeah, change the provider. So here there are a lot of providers and there's an arrow button down here. It will come. You can change it. I'll go through that once again. Don't worry. So yeah, we'll start with the agenda. We have around 3 hours. I'll not bore you too much. We have a good lunch. I'll not let you guys go to sleep. We are going to understand the GPU and CPU stuff. Why is it important? And how it affects the overall LLM development, because we are doing things from at scale. We are not doing things on single GPU. We are going to translate it to multiple GPU and multiple nodes. So it's essential to understand how does things work at a broader conceptual level instead of going into very finer details of GPU, right? But broader conceptual understanding always helps to assess how your things will span out at scale. And then we are going to see very important stuff, which is the data curation part, which constitutes, or which is the moat, kind of moat for LLM development. That's why every other company now in open weight models also try to hide what is the kind of pre-trained data or SFT data they have trained upon, right? So Llama started with initial models, they have opened about the data, but in later series of models, they have now hiding the things. So this is kind of a moat, and this helps you understand the basic phenomena over which the LLM can produce things that we are able to interact with very seamlessly. Then we are going to see like distributed training for LLM. How does it happen at large scale? And then we are doing some small inference stuff. And I'm going to give you a few URLs like build.nvidia.com, which you can ping, this is an API service that you can get results from. There are several open source models that are hosted on this. You can ping the API, get the API key, get the responses, and do some piloting stuff, build your own evaluation benchmarks. So all these things you should be able to do without deploying the models on your systems or without requiring too much GPU. So that's what we are going to see. So yeah, there is another event which is going to happen in March 2026. GTC is a global technology conference that NVIDIA annually does at headquarters in US. The virtual registration is always free. There are loads of talks which from customers like Servam, Zoho Labs, Indian customers, and there are other customers around the world, which gives you some kind of recipe, like what is the kind of practices, best practices around LLM or around the AI in general, and gives you a good idea in kind of layman terms to help you get aligned with the developments that are happening in the AI area. So there's a good conference that you can look forward to. It's not extremely technical like CVPR, NeoReps, where you are going deep dive into specific stuff, right? Like how do you change the how do you improve the optimizers, continual learning, etc. It gives you a broad idea about a lot of things that are happening from, like Jigar presented in the morning, about a lot of stuff around scientific stuff that are happening. And there are vision, video generation, etc. So it gives you a good corpus of videos, talks that you can replay at your leisure. But it's a good conference to sign up to. Yeah. Yeah, let's get started with the actual stuff. So why should you care about this GPU, CPU stuff? So to get the most out of GPU clusters, we need to actually understand how hardware performs. So there are several layers in the hardware which, with respect to the LLM development, that we should be aware of. One is computation, which is generally measured in teraflops per second. So how many floating point operations per second our system can do. And what is the communication bandwidth between GPUs to GPU, GPU to CPU, and one box of GPU to another box of GPU. Because we are doing a lot of operations when we are training the LLM. So we need to understand how do we travel these parameters, how the gradients do travel between different GPUs or different nodes of GPU boxes, and what is the bandwidth, how does it impact the LLM development cycle. Because if your bandwidth is small, it will take more amount of time to travel one bit from one place to another. So you need to understand that part and then make your own assessment about what is going to happen when you're going to train the LLM. Yeah. So we'll start with a question. What do you think, like one floating point operation on CPU, how many seconds, microseconds, nanoseconds does it take? And similarly on GPU, like anyone have any guess, any guesstimate? Like how much time will it take for one floating point operation? Anything like? I mean, you don't need to be right. Sorry? No, it's a bit small. I mean, bit larger. It takes more amount of time than picosecond. So interestingly, it's 1,000 times lesser. So it's 1 nanosecond it takes for one CPU, for a CPU to do one floating point operation. In comparison, GPU takes 1 microsecond. So CPU is essentially 1,000 times faster. Right? Then why do we use these GPUs, which are very costly, very power consuming, need a lot of AC, a lot of data center, a lot of big infrastructure. Right? They are 1,000 times faster. Let's say, how much time does it take for 2048 cross 2048 matrix multiplication operation, let's say in BF16 floating precision for CPU and GPU? Like, is CPU bigger or GPU bigger? Just have your guesses. Yeah. CPU. Yeah, CPU is going to take a large amount. Yeah. So this is the actual numbers, 28 milliseconds on CPU for this matrix multiplication and 0.2 millisecond on. So this is 100 times, GPU is 100 times faster when we are going to do a large amount of multiplication between two precision numbers. So like maybe a lot of you, when you are studying, you might have a good question when you are studying, like which company should I, which CPU should I buy, or should I buy GPU or not, right? Should I have in my laptop or motherboard, if I am building, should I have GPU within that or not, right? That's what we have a lot of questions, and we generally pivot around, like, I do not have much gaming requirement. I'm not playing like big games, FIFA, so I don't need probably GPU for that regard. So CPU, as we saw, one floating point, it's more capable to do things at faster pace. It's like a sports car which has a good high-speed engine, but when it cannot put in multiple people within that sports car, like it's limited 2 people, 4 people at max. So at serial task, CPU is good. If you are going to have an assessment about, like, if your processors are mostly serial in nature, that requires sequential processing, then CPU might be a good ask for it, and GPU might be an overkill. But GPUs are like, you can consider a big bus, which can take multiple people at single point of time and can do parallel tasks very efficiently. So it is optimized for parallel tasks. And why is it optimized? Like what feature makes it optimized for parallel task is this. So there are a lot of arithmetic logical units in both CPU and GPU. The left part is the CPU, the right part is GPU. There are a lot of ALU units which are smaller in size than CPU. That's why CPU was performing one floating point operation in 1 nanosecond. And CPU has larger ALU size, but lesser number of that. So you can think of like sports car, and there's a big bus having a lot of seats in that. This is an H100 GPU. No, this is not an H100. The next slide is. So, and there is two important things in every processing unit. One is the control, and second is the cache. So control contains the registers, which helps you take care of what are the operations that you're going to perform when you're going to feed in data with that. So here, CPU is designed with very small number of powerful and efficient cores, which are good for multitasking, for executing application tasks, managing resources, as we saw in because if you have a web browser in your laptop without GPU, you will see a couple of times like if you are opening too many applications, it is hogging the complete CPU. So it's good for sequential tasks and for multitask also, but they are not for large amount of tasks which require large amount of floating point operations. So larger control unit in CPU optimizes complex logic operations. Larger cache helps you in reducing the data access times. And therefore, CPU tends to prioritize latency over throughput. So there are two kinds of designs, latency-oriented design and throughput-oriented design. So GPU is, of course, throughput-oriented, where they are designed with high number of cores. And even though these cores might be of lower quality compared to CPU, they are resulting in faster computations. And they have a smaller number of controls. Control size is smaller and cache size is also smaller. So even though, so if you have a repeatable kind of task that needs to be done, in those cases, GPU might be able to parallelize you more effectively. So you can now, after some point of time when we discuss, you can probably try to fit this analogy and try to understand why for LLMs and AI-related stuff, the GPUs are more suited. That's because particularly of this reason. Yeah, so just repeating the stuff that we recently discussed. In CPU, there is less number of ALUs, more control, more cache. In the case of GPU, you have more number of ALUs. Yeah. Okay, I will go back here. Okay, so we need to switch back few slides. Many of us are facing instance spinning issue. So once you are on this page, if you are not able to spin the instance properly, then you change the provider. So here there is a list of providers and there is an arrow button here where you can see more providers. You click on that, try to see if deploy launchable works or not. Okay, everyone have tried. Okay, let me ping to the engineering team in parallel, like this is not working. Just give me a second. Sorry? So once you're done, you should see this page. Once you click on the deploy page, deploy launchable, it will change the button to go to instance page. And when you click on go to instance page, it will now spin up the instance, build the Docker, and then you're going to get the access to the Jupyter notebook. So I can ping to them that many of us are facing issue, but it's expected. They told me like this is going to happen. But yeah, I just advise you to just refresh it. It's a new system which is being brought up, and we are a lot of people. I'm really sorry for this, but yeah. yeah. Please refresh the page. You should be able to do. But yeah, anyways, we'll get back to that later point of time, because we are going to put a GitHub and we are going to put this container till the end of the day. around like 8 to 10 p.m. because every hour there is a cost associated with the instance. We have some limited number of credits, but we can spin up let the people who have not been able to spin this up, let them give more time to spin the instance, and you can go to the GitHub and execute the things by yourself, even in that case. So we are putting all the things to GitHub. So yeah. So I hope things are a little bit clear in terms of CPU versus GPU. That's more from the conceptual point of view. These are like, you can just, these are few pointers that you can read. These are not very important. I think the discussion that we do, the questions that you have will be more important. There are like things that you can find on several websites. GPU has high bandwidth memory, more compute resources as we discussed. Even though the latency is a bit higher because the ALU is a bit smaller in GPU, the throughput is expected to be high. So this analogy of sports car and a bus might be more beneficial to understand. But this is only from the compute perspective. We are not discussed yet the communication part. So yeah, what is inside a GPU? So this is 2 warps of H100 SXM. So each GPU consists of multiple SMs. SMs are streaming multiprocessors. So H100 runs at the peak 700 watt power, and it contains 132 SMs. So here, if you closely observe, there is a FP32. These are cores, and then there are FP64. These are again cores, and these are int32. So if you are going to feed a FP32 precision data, it's going to be processed in these cores, right? So I have only shown in this slide two of these warps of SM. I have not defined warps yet, but there are actually 4. So each warp will contain, like, let's say around 16 or 32 FP32 cores. So if you multiply 32 into 4, 128. So one SM contains 128 FP32 cores. And one H100 GPU contains 132 SMs. So 128 into 132 comes out to be around 16,000. So you have 16,000 FP32 cores within your single H100 GPU. And what happens with BF16 and FP8? So for that, we have tensor cores. So all the BF16 related operations will happen on these tensor cores, right? So I guess the hierarchy is clear. There is an GPU, there is a streaming multiprocessor, which are like 132 in H100 and 160 in Blackwells. And below that, there are multiple cores or multiple warps. Inside warps, there are cores. So there are 4 warps in each of these SMs. So GPU, SM, warp, cores. Cores are the most important part. So just to give you another analogy with the CPU, the AMD 9965 CPU contains 192 cores. So these cores are again these, and each core in the AMD CPU can at most process 2 threads at a time. So they can run 384 threads in parallel. But in H100, we calculated 128 into 132, around 16,000. Right? So that's the difference between the throughput-oriented design, which is GPU, more cores, more number of cores, allow more data to be processed, repeatable data, and CPU, which is more latency-oriented, large number of large size ALU, large control size, which can process data quickly, latency-oriented design. So these streaming multiprocessors at the top left SMs are roughly analogous to the cores. Both execute computations, do store state with the registers. So there are registers within that, and there is an associated cache with each SMs. So there are 132. So each cache in the SM is 256 KB. So there are the 132 SMs, so 132 into 256 KB. I know these are a lot of numbers, but numbers remain in your memory more than what we generally discuss in general terms. So that's why I'm telling you these numbers that will help you retain your memory when someone calls Blackwell that has 160 SMs. This is more at the broad conceptual level. We are not going into any detail. But this is how the things get processed at the GPU level. And that's why they are more popular now with the AI stuff. So this is all about computation. Now we are coming back to the communication. So all these slides will be available on the GitHub. Most of them are already. So you can just look at when you're free, you can also look at that. Now coming to the communication part. Because computation is only process those tasks or those floating points which are dedicated for that GPU, right? If you need multiple GPU to to process certain tasks, then you need communication between those GPUs as well. So for multi-GPU computing, there is a library called NCCL. In conversational terms, we call it NICL, which stands for NVIDIA Collective Communication Library. It's a library for providing primitives for inter-GPU communication. And this can be, with the help of this library, we can easily integrate into our PyTorch kind of frameworks, which helps us in doing these multi-GPU computing, like data parallelism, tensor parallelism. So under the hood, PyTorch, this NICL provides that interface to allow it to interact with the between multiple GPUs, among multiple GPUs or among multiple nodes as well. And now there are different kind of communication links that you can have within when you are doing this multi-GPU computing. One is PCIe. The other is, PCIe is again an interconnect, which is peripheral interconnect. Then there is an NVLink, and the other is the InfiniBand. And it's not shown here, but in DGX kind or HGX kind of system. So what happens is you need to communicate from one GPU to another GPU, right? So you need some good interconnect with high bandwidth. So that high bandwidth that NVIDIA provides is NVLink. It has more bandwidth than the PCI interconnect. Okay, so there is a CPU, GPU, and there's a bandwidth. Okay, CPU to GPU is generally through PCIe, which gives you a bandwidth of 128 Gbps, single side. But for NVLink, it's from GPU to GPU, right? So in A100, the effective bandwidth is around 300 gigabytes per second. In H100, the bandwidth is increased to 900 gigabytes per second. Sorry, in A100, that was 600. H100 is 900. And for Blackwell's, the GPU to GPU interconnection is 1.8 terabytes per second. So what happens is you have 8 GPUs in a node. Then you have an NVLink connected to a switch, right? Generally happens with our internet, right? There is a switch or router which makes our packets go from one end to another. So you have an NV switch, which is connected from each GPU is connected to the NV switch via NVLink. That is high speed that I mentioned you, these speeds. And the NV switch routes the packets or the bits from one GPU to another. So this is again inside a box. Now there is a second box. How do you connect one box to second box? You have Ethernet, right? This is the most popular way to connect internet from one place to another. So apart from Ethernet, NVIDIA built a link called InfiniBand, which is more optimized or more oriented. There are certain primitives that are specifically for the AI, which has lesser bandwidth than NVLink. So InfiniBand, I think it's 600 gigabytes per second. As I mentioned, the NVLink is like 1.8 terabytes per second. So InfiniBand is the connection from one box to another. That is still smaller, but is more optimized than Ethernet. Okay, so there are three things like PCIe from CPU to GPU. GPU to GPU is NVLink. One box to another box is InfiniBand. So why I'm telling you all this stuff? Because you can actually see on your terminal. So if in the later part of the presentation, once you are able to log into the system, you should be able to see like NVIDIA SMI, which is a very popular command for system management for GPUs. You can see the topology also, like how each GPU is connected to another GPU with how many NVLinks. Okay, so now in multi-GPU computing, we have covered CPU stuff, GPU, what constitutes a GPU, the NICL library, and now how does NICL library helps you in doing the training of LLM, right? So that's the path we are following. So there is this very popular operation, we call it reduce scatter. So when you're going to train a GPU, when you're going to train a model on a GPU, on multiple GPUs, you need to, so let's say your model is able to fit into a single GPU, okay? So now you're running multiple copies of the same model on different GPUs. Now you need to aggregate, once you do the forward pass, you need to aggregate this, the values that are passed to each copy of the model. And then once you aggregate, you need to distribute or broadcast the aggregated values to other GPUs to keep all in sync. Does that make sense? Okay, I'll repeat. So what happens is, let's say you have this one GPU. There are 4 GPUs here. Now, each is processing a different copy of the data So each GPU is processing different copy of the data, right? And once each GPU processes the copy, it has certain values here, right? Now you need to broadcast this value. This second GPU need to broadcast this to first, third, and fourth, in order to ensure that all the values are in sync, because you need to do a second operation after that, which is back propagation, right? So the forward pass should propagate or broadcast the same set of values to ensure everybody is in sync, right? So how does it happen? This happens through reduce scatter operation provided in nickel library. Does that make sense? So this reduce scatter operation actually reduces the sum provided by each data copy which is stored within a GPU, which is passed to the GPU, and then once it stores, it broadcasts to other to do this reduce scatter operation. So it reduces and then scatters. That gets broadcast, right? Then there is another operation which is all gather. So what happens is, once a model layer parameters, let's say they are sharded across GPUs, the GPU 1 contains split 1 of the model parameters, 2 contains split 2. So the model parameters are splitted, or model is split across different GPUs. Then what happens is, before a computation like forward pass, an all gather collects. So like if you see here, it collects all parameter shards, so every GPU can proceed, because you need everything to be sync, because you can do the independent operations on GPUs, right? But you need everything to be in sync to perform the next set of operations. So for that, we need this all gather. And once you combine the reduce scatter and all gather, you get all reduce. So this is all useful in distributed training, because you need to have different kind of parallelism techniques to ensure that your model can leverage different GPUs, can leverage different nodes within your cluster. This helps you, these communication primitives provided by the nickel library helps you in doing all this stuff, right? So this is more about communication, right? And there is all to all, again, combining the all reduce operation with all gather to get all to all. Now coming to the part, how do I see? We have all seen the concepts now till date, right? Till now we have seen the CPU, GPU, the computation, how many teraflops does it take, the communication, which library provides you those communication primitives or APIs to help you doing that stuff. Now we'll see, how do I see it? How do I know कि भाई ये हो रहा है जो is correct or not? So in your systems, you will see NVIDIA SMI, which is a very popular command. With NVIDIA SMI, you supply this topo minus m. So the topo stands for topology. So NVIDIA -SMI space TOPO minus m, right? Here it's written. So what you will see in this case is, let's say if you have a cluster or if you have a single GPU with you, what you will see is that GPU 1 is connected to GPU 0 is connected to GPU 1 via NV12, right? So NV12 is 12 links of NVLink. Similarly, GPU 0 is connected to GPU 2, 3, so on, so on. And this is via NV switch, but for the sake of clarity, we'll assume like they are connected all together. So there are 12 NV links. Each NV link has a bandwidth of 50 gigabytes per second. And similarly for Edge 100, you can see they are connected via 18 NV links. So 18 into 50, it's 900 Gbps, right? So that's why we are coming out to be 900 Gbps. Now you will see like there is a PCI interface which is connecting one GPU to another set of to another CPU, right? Through via NIC, there is a PXB link which refers to traversing multiple PCE bridges to connect to the host. Host is CPU. So you will see that complete topology. You will be like more confident in like what is your system constitutes. If some vendor gives you something and then you are not able to see, then you can contest, right? Okay, I'm not able to see this, correct the system. And again, this for B200, they are connected with 18 NV links, similar to H100, 18, but this NV link generation itself is different. So this NV link generation has 100 gigabytes of bandwidth. So 100 into 18 is like 1.8 terabytes per second. So this is how you can to the conceptual understanding, and also can see in your systems. So if you are able to log into the system, if you see run this command in your system topo-m, you'll be only able to see single GPU. So there's no NVLink associated with it, right? If you spinned up the 2 GPU instance or 8 GPU instance, then you would have seen this kind of metrics in your output. Yeah. So what is NVLink? We have been talking about it, and which is the key part for AI related training. So in multi-GPU systems, it has a bandwidth of to like now 900 gigabytes per, or 1.8 terabytes per second, and it lets GPU talk to each other via NV switch. And yeah, it is highly, it seems like all the GPUs connected with each other are like running with a single large amount of RAM because of this high speed interconnect between the GPUs. So you will see like on the surface, it's if H100 has 80 GB GPU memory and you have 8 GPUs in a node, so you effectively will see like there is 640 GB of memory in your whole system because of this high speed interconnect with lower latency. And okay, so we'll not probably go into the lot of algorithm stuff at this point of time, because this basically tells you like if your boxes which contains these 8 GPUs, these nodes, how they are interconnected with other nodes. So there should be some algorithm which allows you to pass information from one node to another, right? So there are a lot of nodes, each node containing 8 GPUs. Let's say you have 128 nodes. These are connected with some sort of algorithm so that you can pass the information from one node to another in a very less amount of time. So these are like algorithms. They are ring algorithms, tree-based algorithms, which helps you do that stuff. But we'll probably not go into this because of a lot of stuff that we have to do. Yeah, this is probably what we have discussed. Each GPU is connected with another GPU in a node via NVLink, and one node is connected to another node via InfiniBand kind of network, which is again based on Ethernet kind of primitives. So yeah. Now if is anyone not able to start the systems yet? How many of you? A lot of you. So can someone share like what is the exact error? Okay, let me also start in. Okay, few of you are able to run, right? A lot of you. So Vivek in the group, Vivek Vishwanathan, you are able to run? No? Okay, but why is it showing here ki you are able to run? Lokesh, sorry? It's still deploying. Okay. So it's in the deploying stage, right? Or you are not able to, it fails. Okay. Can you go to this GPU page? Sorry? Yeah, live demo we'll do that because I have my instance running. So once you go to this GPU page, you should be able to see something like this. This is running and this container is built. So once you click on this, you will get a access tab here. And when you click on access tab here, you should be able to see this link, tunneling link. This is actually the Jupyter Lab launch link. How many of you are able to execute it? Oh, 3, 4. It's showing a lot of people. Can you confirm once, like in the GPU page, are you able to see this container, which with this state running and built? Okay, let me create another launchable for my side and see like what is happening. Okay, it's not giving me this. Okay, I'll show you the live demo. Probably there is quite a good number of issues with this. Okay, let's try it one more time. In my case, I'm not able to see the launchable itself. Yeah. Okay. So I have one instance running at my end. So let me show it to you live probably. How does it look like? So NVIDIA SMI, as we know, is a popular command. This will show me multiple things here. One is this is my GPU. This is connected via PCI interface. As I mentioned, this is a very popular interface for connecting from CPU to GPU. It has this much amount of virtual RAM with me, 80 GB, and I'm consuming like 4.5 GB around from that. When I do NVIDIA SMI topo minus M, since it's single GPU, it will not show me much information because I'm not connected to another GPU via any link. This is a separate instance altogether. Yeah. Yeah, if you are not, most of you are not able to do it. So, yeah. It's 200, they will not get a chance to do that because okay, they're saying it's able to do. Let me try H200. Give me a second. It's I'll show you how to create launchables itself. So these launchables are again Docker containers which I provided while launching the system. So this is similar to like how you create spin up instance on different clouds, right? If you have used some clouds, GPU clouds, um, you should be able to do. Okay, I'm not able to launch in Yara. What should I do? Yeah, yeah. I see. I could create another instance, H200 type of instance, but I'm not getting the launchable itself. Anyways, um, okay. Apologies for that. Okay, I'm able to get it now. Give me a second. I'm just uploading the Docker Compose file, which will allow you to spin up another instance. Okay, so this is an emo container, as you can see here, with the exposure of port. Okay, so I'll select here H200 instance. Select some provider. Yeah, so if you refresh your launchable page here, you should be able to see another uh, instance with the name H200. I think few of users created your own launchables. Actually, it was not supposed to be created. Okay, we'll come back to the presentation now. I think we are devoting too much time for this. Yeah. So here you can see the topology. Because it's a single GPU, you won't be able to see. So this is more or less from the computation perspective. Now let's go to the point of view of data curation part. I think we'll now go to how do we develop LLMs. Okay. Yeah, we'll pause for a few questions. Like, yeah, sure.
Why has NVIDIA disabled NVLink in its consumer grade graphics cards?
Consumer grade graphic cards. See, NVLink was not supposed to be there for consumer link because it's a single GPU in consumer NPCs, right? So it was. I don't think it was enabled at all. Not sure about that, but okay. I don't know the answer. Yeah. Any other questions, please? So any questions from the streaming multiprocessor compute cores? Yeah. Can you speak?
Hello. Yeah. So when we use a floating point 32 in any code, and then we have floating point 64 or 16 as well, and then we see that in the GPU utility is showing 100%. That means only all the floating point 32 is getting used.
Right. So those respective cores. So the question is like we have cores for int FP32, FP64, or tensor cores for BF16, FP8. When it shows like 100% core is being utilized, when we run a process with some particular precision, does it refers to a complete GPU occupation or that particular core, right?
Yeah.
So that is with respect to that particular core.
So is there a way when we can use the mixed precision or in AI, right?
Right. Yeah, so when we use mixed precision training, so that's why if you see the latest NVIDIA GPU like Blackwell's, they do not have FP64 cores at all. So the FP64 cores that you saw in the in one column, that is not at all in their Blackwell's. So they are making more space for tensor cores to ensure that mixed precision is processed more faster in the GPUs.
So let's say if I always choose the floating point precision to be FP64. So is there a chance that if I keep using the same core over again, the FP64 gets bad by time, but FP32 cores are still intact? Like hardware degradation.
Yeah, that's an interesting question. So the question is like if you use single gear in your car more frequently, like you drive in first gear or second gear, like in Bangalore traffic, will your gear will be get affected? So yeah. I mean, I cannot comment from the electronic point of view, but I don't know, like if it get bad or not from the because we need to go at the nanometer scale on which was used to fabricate those cores. So not sure about that. Yeah, but good question.
I've got a question on CUDA cores.
Yeah.
So are CUDA cores tensor cores or are they virtualized cores?
CUDA cores. So I do not have a clear answer to this question, but I believe the CUDA cores refers to these different type of cores.
Okay.
Okay. So these could refer to like the tensor cores also. These could in other cases FP32.
Okay. In general, it refers.
Yeah. In general, it's a general term for CUDA cores.
All right.
But each core consists of these kind of smaller cores.
Yeah, excuse me. So
Yeah.
just one question. So in NVIDIA has certain GPUs which are kind of recommended for images. Like you have something called RT cores.
Right.
So what's the difference between RT cores and tensor cores?
So what happens is we have a dedicated So there are two kind of libraries which are more prominently used in images or videos, which is encoder and decoder, right? So you encode the image, you decode the image, etc. So for that, there is a special library, we call it NVEnc, NV encoder, NV decoder. So what happens is for these kind of processes where there is a lot of encoding and decoding happening, there is a separate block in the hardware itself that is made for these kind of processes. So that's why we call it this. I don't know if RT core and NVEnc and NV decode are same or not, but this is what I'm like assuming, connecting the dots for these kind of processes. Yeah. For LLMs, can we use? Yeah, yeah.
That's where I saw that it has something called Tensor RT course.
Tensor RT cores. I'm not sure about Tensor RT core specifically.
No. I think you are mixing few things. Sorry about that. But generally, how it comes is NVIDIA evolved as a gaming company. If you recall, 1992 we started. Till 2005 we were gaming company. So our GPUs were used only for gaming, and we are still leading the gaming part. Then these GPUs to be used for scientific computing, we came up with the CUDA layer. Now CUDA works on tensor cores more efficiently, and that's where the CUDA same works on RTX also. So what you can do here, you can do there also. The performance and many things are in question, but generally all are deployable across all GPUs. And that's where for scientific computing, we have this series called A100, H100, Blackwell, what we are talking today. And these are the good for scientific computing, particularly all LLMs, and end of the day, it's a matrix multiplication, right? Whatever Ayush was showing earlier, communication all to all reduce, all, if you solve any matrix multiplication, everything you apply there day to day. So that's where these GPUs are good for that. And now with the time, we are coming down from FP64 to FP32, FP16, 8, now 4, BF16, all those options we are providing in these GPUs, right?
Yeah, please. Yeah. So until we reach the mic, I hope the mind map, whatever takeaway we have spent 1 hour on this, so I hope the takeaway should be there when you go out from this room. Like, what is the mind map of CPU, GPU, the hierarchy of GPU, the communication, computation. I hope that makes sense. That should be a good takeaway. Yeah, please.
Thank you. Great presentation. Thank you. So, this is Rajesh. I have a CPU with an RTX A4000.
Right.
Can I run an LLM on it, or what would it take for me to set up a GPU at home?
That's a good question. What does it take to set up a GPU at home that can train LLMs? So there are two different paradigms to it. RTX can certainly do it. That can train, but it may not be at the expected speed. So you will get frustrated at some point of time. But you can learn many things by building a smaller model, a very small model, let's say a few million parameter model with few billion tokens. Let it run, put it into good AC so that assuming it will not catch fire, hoping that. And yeah, so that's one way. But you can, of course, try to do that. Try not to fire. Try to set up things, because we should also try to leverage more things, because we always see the temperature out of it and then we can stop the processes. That's the common way. The second part is, what does it train to, what kind of GPU does it take to train an LLM? So as we discussed now, this I hope you all can also answer this question. If your GPU contains these many number of cores, okay, these type of cores, these number of streaming multiprocessor, so that you can launch these many multiple processes, right? So when we see like 16,000 parallel cores are there in the GPU, in single GPU, that means you can, assumingly you can do one floating point operation with one core, okay? So you can do 16,000 kind of floating point operations in one clock, okay? So the GPU and CPU has a clock cycle also, right? It can do that number of operations or cycles within 1 second. So LLM generally requires you to run at larger processing speeds, both from the floating point perspective and communication perspective. But I guess A100, so coming back to the question, like what does it take to set up at home? So now coming to the power requirement. A100 has a power requirement of, I think, 300 watts. H100 has 700 watt. And Blackwell's is again 900 watts or 1 kilowatt to that level. That's a peak power requirement. We generally run ACs at 1.5 kilowatt or 2 kilowatt, right? So you need to have that plug and that cooling condition around it to make that GPU run on your homes. We generally do not advise it to do. We generally, in our labs, in our ISC, we'll have a lab where all the cooling requirement, power, etc., fire conditions are satisfied to make these A100, H100, B200 kind of systems running. So RTX is a good way to start, but yeah, putting a A100s at home, we will be at risk.
Right, thank you. The follow-on question for that is, we talked about the data transfer using the NVLink. And in a situation where I set up a GPU and I want to access on my phone, could the 5G network or any other mobile network be supporting for that?
So you're saying,
The data transfer,
can I
yeah.
do data transfer using these some other networks,
Correct.
some other wireless networks?
Correct. So accessing this GPU remotely.
I mean, point number one is you need to have the libraries to allow it to transfer data from one point to another. I'm not sure if they're already deployed, but yeah, Manish.
Full ecosystem should support, that is one. Then second is why you want to do. These questions are very good to ask. But what is the objective behind
That's a
that?
good question again. So let's say that we work in a model where the data privacy is very critical for us.
Okay.
And we wanted to ensure that the entire data that goes into the system just is for our eyes only.
That is fine, but then I appreciate, and there are many financial institute, many government defense institute and all, they do the same. And that's where sovereign India came into picture. All might have heard that word, that India data should remain in India, and then sovereign could be relative at national level, lab level, and anywhere. Now with that inside lab, you can set up everything, but that, I mean,
The
to
inside
solve
that
that
we can do
doesn't
it,
make,
but-
it doesn't make, that is not the answer. What I mean is, at home you set up lab, or you have these network, because that is not made for that. Now you want to try that, it's good, you may face some challenge, but ultimately you will get success. That is not a problem. But ultimately why we are doing that? There is a provision to do that, and I appreciate your security issue. That is okay.
Now,
That is
while the home is an analogy, but what I meant exactly is a small lab.
Yeah,
that we
in
set
lab,
up,
then
yeah.
you can have proper network, no? Maybe he's shown 3 network, Ethernet or InfiniBand. You can have some network and you can transfer that.
So you mean to say through the internet?
Yeah, Ethernet is more secure in that case.
Ethernet, not
Okay.
internet. Ethernet, we are talking Ethernet.
So that's a local network.
Local
No,
network.
so
For
we are
security.
moving away from the local network. Let's say that I access it from a different geography itself, another country. So
Then generally what organizations do is they do a dedicated optical fiber line from one point to another.
yes, yeah.
So that's what they do generally to make systems more secure, more these kind of works.
All right. Thank you.
So overall the question is what are the different ways we can connect GPU to GPU? Can it be done via wireless? That's an interesting question, but yeah, thanks.
You have?
But I hope that the things make sense to you. The mind map is clear. That's the objective of this.
Okay, one more question, then we will go back to presentation. We'll talk during.
Yeah, it's less of a question, more of a advice for later. So I just want some resources where I can learn L1 to L3 cache optimization, code written for better LLM training. Any resources for
Yeah,
that?
we'll go to
later on.
in this presentation,
All right.
the second part. So we have been advised to have a break in 15 minutes. So we'll cover now how do you develop LLMs. So there is, as we discussed previously, data is the most important part. So first is you curate the data, you collect the data, then you curate the data, improve, have some tags on the data like this particular sentence or document is high quality, low quality, medium to low quality, medium to high quality of this language, etc. So once you have that, once you have a clear understanding that your data is in place, and now coming to the question like how much data do we need to train an LLM, right? So that's a more subjective question. It depends on the objective, that how do you want your LLM to behave. Let's say you only want your LLM to answer in Kannada. Okay, then do you need data in English or not, right? So it depends on the end objective which decides your whole process. That generally happens in life as well, right? So the path that you take depends on where do you want to reach. So generally, the kind of LLMs, open weight LLMs or closed weight LLMs that we see are trained on trillions of tokens. So trillions of token constitutes the data that is written by humans on web. So on web, you see most of the data is in English, and now it's in Chinese also, Japanese, but relatively less in our Indic languages, right? Due to Unicode issues in the late 90s, we are not able to standardize the Unicode format for our languages. That's why we'll have relatively lesser presence on the web, which constrains our ability to train data, to train these LLMs in the initial stages, right? We are already past, OpenAI is 3 years beyond after the first launch of the model, right? And even before 3 years before launching, they would have been working, right? Transformers were released in 2017. So we are already late on that trail, but better late than never. So that's why Government of India is also trying to do things in our own Indic languages so that we'll have more data to train LLMs. And of course, it's from the strategic perspective as well. But overall, gist of the discussion is we need trillions of tokens to train a good LLM. These trillions of tokens could constitute human created data, synthetic data generated by some other LLMs, right? That will be used because you can now, these LLMs now have the ability to impersonate as a different kind of persons, right? You can ask LLM, you be a cook, you be a teacher, you be a academician, completed PhD in ISC. Now you answer this question, right? You can ask the LLM to behave or emulate the behavior of some particular person, right? Or particular type of person. So that's why you can create different kind of data to cover that tail distribution. We generally have this understanding or have this assessment that LLMs are not able to cover the diversity of our Indian culture, right? So by creating these personas by the LLMs on the various tail distribution which is not covered by the LLM well, let's say if Tulu is not covered in our, some person who is talking in Tulu or in Kannada is not covered well or is not represented well in the output of the LLM, right? Can you adapt the LLM to do the behavior well, to do the well-defined behavior for this person? So now you have that ability to do. So that's why this closed source LLMs are now, if you use Perplexity or any kind of code-based LLMs, you see these open weight LLMs are not very close to these open weight LLMs performance, right? Apart from DeepSeek, which is a very large model, most of the open weight LLMs have surpassed because of this data that they have curated, collected from different organizations around the world, private data, public data, synthetic data, due to which they have been able to create these LLMs. So this is the first exercise, create data, and then you do pre-training. So for pre-training, you need libraries. One of the biggest or most popular library is PyTorch. PyTorch gives you different options to do LLM training on different GPUs, on multiple nodes by leveraging these underlying libraries that we discussed, nickel kind of libraries, right? And then once you are done with the pre-training, you do some continued pre-training on top of that so that your LLM adapts to your domain or is more performant, having higher quality outputs. And once you do that, then you adapt the LLM to produce outputs in a more likable manner. RLHF is one technique, reinforcement learning based technique, which adapts the LLM to produce output in the way the human likes. So these big these closed model companies are investing a lot of money on this RLHF. They constitute around like almost 10% of the compute that is spent in pre-training. So you can just make a guesstimate now, like you have trillions of tokens, you have billions of parameters. Now, that's on the pre-training part. And once the pre-training is done, you need to do RLHF, which is now 10% of the compute, even though your data in the RLHF is like millions of tokens or few billion tokens. Because you need to do a lot of repeated experiments to ensure that your model is producing the output as likable or as in the way that is expected by the humans. So yeah, as we discuss, building foundation models require you to have mountains of training data, large-scale compute infrastructure, and of course, you need people who have expertise in several fields, like infrastructure. You need to set up infrastructure in a proper way, such that when you train the LLM, your things don't get stalled. Then you need people at the engineering level which are working at these core libraries which helps LLM to train, right? So underlying PyTorch, there are several frameworks which help the model to communicate to GPU. Like CUDA is one framework which helps the software layer to communicate to GPU. And then you need for the communication perspective, etc. Then you need AI engineers or model developers who work at these model development level. Then you need these application development people who build these applications on top of these models, right? So you need different set of expertise, deep technical expertise to train these models. Yeah, so this is what we have discussed. Now, what are the libraries that help you in doing all this stuff? So NVIDIA has a framework, NeMo framework, which stands for Neural Modules, which is an open source library, Apache licensed, which helps you in doing all this stuff from the data curation, that is cleaning the data, pre-training, preparing the pre-training step for your model, doing the post-training, which is the RLHF part with different algorithms for both the language models and multimodals. Like you have an image modality or video modality. So this library helps you in doing all this stuff by managing all the underlying stuff, by giving you simple wrappers. Like as we move forward, we have now several libraries which are helping to build wrappers, right? We are mostly coding in wrappers now. We are calling some library which has already developed the functionality which we intend to introduce, and then we just call that library and we are done with the stuff. We are not so these NeMo is again a wrapper which helps you in doing all this stuff related to managing the parallelism part, the large scale part, and so on. So now I think we'll cover this part. I think we have 5 minutes. So this is one library, again by the NeMo framework, Megatron Bridge and Auto Model. So this helps you in doing quick experimentation. Let's say if you have an 8 GPU cluster, 8 GPU node with you, then you need to do a lot of experiments before training your final model, right? So you can build the prototypes, do faster experimentation with the help of these libraries, because these have inbuilt recipes. So let's say Llama has trained on 8 billion parameter with some architectural configuration. So you can directly import the recipe of Llama. It is inbuilt within this auto model itself. So this is again a wrapper on top of these Llama, Gamma, and Quen kind of model architectures that will help you prepare the pre-training stage quickly. So yeah, I hope it's visible. So that's how easy it is. I just wanted to show you from the screenshot. So we have creation of config. So here what happens is, in this config, we are instantiating the Llama 8 billion parameter model. So here if you see the tensor model parallel size, pipeline model, context parallel, and so on. What is the global batch size and so on. So these settings are again borrowed from the Llama architecture itself. And you can, of course, modify it because it's just a YAML file. And you have the optimizer, what is the learning rate, what is the decay that they have used, etc. and so on. So the open models, when they have disclosed their architectural and strategy, you can just import this YAML file for any kind of open model, and then you're good to go because we have already prepared the data, and thus we just have to launch the process with this YAML file. So we don't have to worry about all the implementation at the granular level for tensor parallelism, model parallelism, etc. And this gives you various benchmarks also, like this library I'll show probably after the break, like what is the expected kind of teraflops that you are expected to achieve while doing this training run with this particular model. Because you need to do a benchmarking, like the setup that you have is close to what the actual original setup was. So this helps you in doing that stuff as well. Yeah. Okay, so right now we'll have a 15-minute break. After that, we are going to, in the meantime, we are going to solve the issue that you're all facing about launching the instance. And then we are going to go into the data curation part, like what are the stages that are there in the data curation part. So yeah, we'll stop for a 15 minutes break.
Guys, 15-minute short break. Anyone who is facing problem, we'll solve it during the break. Others, please proceed for the break, coffee break. 15-minute max.